Okay, so 10.1 day 2, the formulas, well, the formulas are just right there on the board. So x, y are just functions now, like that. And then dy dx, which of course measures slope, is actually dy dt over dx dt. And then d squared y dx squared, which measures concavity, is d dt of dy dx over dx dt. And lastly, the length of a curve in parametric is integral from t1 to t2 of dx dt quantity squared plus dy dt quantity squared. So the good news about this chapter is all of this is very formulaic. You can actually just run through and just use the formulas. There's a little bit of critical thinking, like which formula should I use right now, that kind of stuff. So I'll try to help you with that. But let's just write down what these measure. So the formula, this formula measures what? Coordinates. This will help you find the actual coordinates of a point, right? So if your curve is kind of goofy, you can find the coordinates here, right? By the way, parametric functions can be quite silly looking. Okay, you'll see that in a minute. I can actually do a Google image search of parametric graphs, and you'll see there's all sorts of crazy graphs out there, way more interesting than your typical XY graphs. Okay, and then dy dt, of course, measures slope of tangent line. So if this is your curve, it can measure the slope of this line right here. Right? D squared y dx squared has always measured concavity, and it still does. So what is the concavity at this point here? You know, probably concave down, I would say. Yep. And then the last one, of course, is length. So that measures just a portion of a curve. Okay? Question?
On the board it says traversal. Is there
Yes.
instances where it's going to be more than that?
Yeah, okay, so what can happen sometimes, as I explain this next example, I'll mention this again, right when we get to the length calculation comments. On an example, we don't actually find the length, but I want to make some comments about length. So let's get into example 1, and you'll see kind of where that goes. And I will answer your question. So we actually all we did last time was just do a little bit of plotting. Morris said it was kind of too easy. That's because I was getting the pre-calc part done, and I knew I only had 15 minutes. But the pre-calc part is you just plot it out. You just plot the points. And you see what it looks like, right? So you don't really need to plot because your calculator is so powerful it can actually do that for you. So let me show you how you can do that. I'll pull my calculator up in a second. For this first example, let's consider x equals t squared minus 5 and y equals 2 sine t. And for times, or whatever t stands for here, probably time, that's between 0 and pi. Okay? So you could do this by hand, kind of sketch it out, but it's a little bit awkward because if you make a t, x, y table like we did last time, you'd probably pick times like 0 pi over 4, pi over 2, 3 pi over 4 pi. But calculating the x is a little awkward. The y's are actually pretty simple. The y's just go 0, root 2, 2, and then root 2, and then 0. Those are not too bad, but the x's are kind of ugly. Take a look at your x's. Your x's are going to be like 0 squared minus 5, pi squared over 16 minus 5, pi squared over 4 minus 5, etc. 9 pi squared over 16 minus 5, pi squared minus 5. I don't even know what these numbers are, right? But one thing's for sure, our starting point is at negative 5, 0. And our ending point is at pi squared minus 5, comma 0. So let me calculate at least pi squared minus 5. We'll just have one point. The calculator will do the rest. So this is at 4.870. Okay, so if I had to graph this, kind of to see the motion, and I was doing it by hand, I might just plot 2 points or 3 points at most. So it kind of started over here and it ended over here, see? So it starts here, ends here. And you could tell by the point, like pi over 2 right there, it actually was traveling this way. So this is kind of what the motion looks like. Okay, now you can actually graph these on the screen. That's what I was saying. So what you want to do is turn on your calculator. I don't know why I always say that. It's kind of obvious. If you don't turn it on, then, well, does anyone know where the on, not know where the on button is? Everybody knows where the on button is? Okay. You want to go under mode and change it to parametric, right there, PAR. Also make sure it's in degrees because there was a sign in this problem, right? I meant to say radians. Put in radians because there's a sign in this problem. Okay, now you'll notice when you press y equals, it doesn't say y1, y2 anymore. It says x1t, y1t, etc. I'll enlarge it here so you can see it better.
What are those hash marks?
What's that?
The hash marks.
Oh, yeah. So these little marks over here tell us that the type of graph it's going to draw. It's going to draw like a connected graph. You can actually change that. Watch. You can go over to the left a little bit and click on that, click enter. And you can make it thicker, or even, I don't know what that is. You can make it dotted, like a dashed curve, you know. But normally we just keep them the same as the default, you know. Okay, let's put in our x. So our x is t squared minus 5. You'll notice that now your x button doesn't say x when you push it. When you press it, it says t. And then the y is supposed to be 2 sine x, so, you know, 2 sine t, I mean. Once you enter those, there's one more thing you have to do before you press graph, okay? If you just press graph now, you're going to actually see too much curve. This is not what we want. Remember, we had a start and a stop, right? So what we need to do is go into window settings, and we need to make sure that it goes t min 0, t max, pi. Why am I choosing pi for a maximum t value? It's given in the problem, right? Yeah, so that's important. You have to limit it. You don't want to give the object too much time to travel, or you'll see too much of its path. Okay? All right, so now you can press graph. The zoom button still works. You can zoom in, you can zoom out, whatever. You know, you can trace still. But go ahead and do me a favor, press second calc. You'll see this menu has changed quite a bit. This menu used to say fmin, fmax, zeros, whatever, dy, dx. This menu is definitely new under F4, second F4. There's some new stuff there, isn't there? In fact, it's very limited. So this just means that it's harder for a cheap calculator like this to handle parametrics. It's harder to handle parametrics than regular functions. Okay. Okay, so let's go back to here. We can see our sketch, our initial sketch is pretty good. What can the calculator not tell us? What can the calculator not show us that my sketch does show us? My sketch is a little better. It has a couple extra details. What does my sketch have that this sketch doesn't? Direction. What else? Yeah, you can't tell from this image here what is the starting point, what's the stopping point. See that? Whereas on mine, because I made the table, I knew that it started at 0, 0. Okay? All right, I should say negative 5, 0. Okay, so just know the limitations of parametric mode on your calculator. And now let's go back, and that's kind of like part A, just plot it, you know. So now let's see what else we can do with this thing. What else do you think we should try? Oh, questions first? Go ahead.
My calculator, it has...
Okay, so T-step means you're going to tell the calculator how often to plot a point. Okay? So first the T is going to invent, the calculator is going to invent these T values. So the calculator is going to come up with its own T values, and you're just going to tell the calculator how many points to plot between t equals 0 and t equals pi. So if you change your t step, keep it small. Okay, some people like a real small t step. But under window, he's talking about this third entry here, t step. Mine's at 0.1308996, which is pi over 24. Okay, so this is pi over 24 right here. I figured that out once. That's what that is. But you can make it smaller if you want. I wouldn't make it too much bigger, or it'll look kind of jagged. Your graph won't look that great. Good question.
And then I just want to see, can I kind of look at it?
Yeah, yours is a little different. You got that Inspire. Let me see it. Okay, so one of two things can happen. The particle can either keep going, or it can recycle. So sometimes it will go start to end, and then back to start, and then back to end, and back to start. Or sometimes it will go past the ending point and just keep on going. You know, you can actually use negative t's if you want, but I don't think it's very meaningful in a physical situation if t means time. Okay? So, all right, so there it is. And let's go now to our second question, part B here. So what else can we find? Let's find the highest point on the curve. Find the highest point on the parametric curve, or the plane curve, it's sometimes called. Okay, so what you're looking at is a graph of x and y. Okay, so don't think, oh, this is like a t graph or something. It's not. This is x, this is y. T was just a controlled input to map this out. So we're still interested in what we've always been interested when we are trying to find a maximum point. We're still interested in dy dx being 0. So what's true about this point right here is that dy dx is 0. That's still a true statement. You know, just because we're studying a new type of graph doesn't mean maximum means something new necessarily. So I want to find that point right there. So I'm going to set dy dx equal to 0. Okay, so set dy dx equal to 0, and you'll notice that the formula for dy dx is a little more complicated in this chapter. Dy dx is actually dy dt over dx dt. Okay? Now, if a fraction is equal to 0, a over b equals 0, whose fault is it, the top or the bottom? The top, right. So a over b equals 0 always implies that a is 0. So what we're saying is, yeah, we can just treat this as dy dt as 0. See? And that makes the problem a little bit easier than dealing with dy dx. Okay, so dy dt means derivative of 2 sine t dt, right? Okay, so this just comes out to 2 cosine t, no big deal. So we seek answers between 0 and pi, right? So don't get crazy here. Just pick the 1 or 2 values between 0 and pi that make this true. So can you think of a value that makes this true? T is what? Yeah, I think pi over 2 is actually the only answer. Okay, so I'm going to go and write only here to remind us that whenever you solve a trig equation, you might have more than one answer, just not in this case because of our restrictions. Right, we were told to stay between 0 and pi. Okay, one answer. Interesting. That actually makes sense graphically, too, that there's one answer. How many highest points do you see here in this picture? 1, right. We should not expect more than 1 t value, unless this thing doubled back on itself. Okay. Is this what they asked for? For us to find the t value of the highest point? Is that what the instructions say?
No, it says find the highest point.
It says find the highest point, right. So what we need is an equation or a set of equations that can help us find the coordinates. So that would be just this first one, right? Right here. X and y. They were given to us, right? So let's go back and plug this into our x equation and our y equation. So x is pi over 2 squared minus 5, which actually comes out to about negative 2.533. And then y is 2 sine pi over 2, which of course is just 2. So the coordinates are negative 2.533, comma 2, which actually fits the picture perfectly. If you look at the picture, about negative 2.5 up 2. Worked out good for us. Okay, what else could we study? Well, we got the highest point in the graph. Now let's go ahead and find maybe the points of inflection or something. Could do that, right? Okay, so let's go on to part C. Find all points of inflection for the plane curve. Right? Okay, so you guys remember a point of inflection is a point, so recall, a point of inflection, you got to know the definition perfectly, okay? It is a point like this, or even like this. Okay, these three drawings are very important, okay? Point of inflection is not necessarily the point where the derivative, the second derivative is 0. Okay, don't memorize it that way. The truth is, the graph has to change concavity. Okay? It has to go concave down, concave up, or vice versa. And you have to be able to draw a tangent line. So if you look at this third case, what do you notice about this point right here? That's a point of inflection, but it's at a what? A vertical tangent spot on the graph, right? Which means the second derivative actually doesn't exist, but it's still a point of inflection. So the best definition is it changes concavity. And it's not a cusp or something, okay? You can draw a tangent line there. Okay, so recall what POI looks like. And let's get busy here labeling these. So this is F double prime is 0. This one is F double prime is 0. This one is F double prime doesn't exist. It's undefined. Okay? So what I'm going to do is I'm going to find the second derivative. I'm going to set it equal to 0 and undefined. All right. So my strategy, set F double prime, or in this chapter we kind of usually just use d squared y dx squared. Set this equal to 0 and undefined. Okay, if you look at the formula for d squared y dx squared, it's actually harder than you think. Okay, you cannot just say, oh, I found the first derivative in the last part of the problem, I'll just take the derivative again. It doesn't work like that. Okay? First of all, you have to understand that d squared y dx squared means the derivative with respect to x of dy dx, right? And if you're going to take the derivative of something in parametric world, you have to use that dt. So the rule is actually this: d dt of dy dx, which you found in the previous problem, all divided by dx dt. There's an extra dx dt that surprises some people here, but it's important in the world of parametrics. Okay, so let's get busy here. We found that we actually never fully found dy dx in the previous problem. So let's go back. We need to find dy dx first. So dy dx is dy dt over dx dt, thanks to the chain rule. You can see those dt's almost cancel out there, don't they? Okay, so what is d dt of t squared minus 5? And what is d dt of 2 sine t? See? So what's the top? The top is, well, the top is just the derivative of t squared minus 5. So what's that? Just 2t. The bottom is 2 cos t. You can cancel out the 2's if you like. Okay, so that's going to go in right here, see? That's dy dx. That's where it goes, into the top of the second derivative formula. Okay, so we're going to be plugging that in. Yes.
Why did we put dx dt is 2 sine t when that's dy dt?
Do I have it upside down?
Yeah.
I have it upside down. Sorry.
So
I scrolled down and then I lost my place there. Yeah, because I couldn't see my work up above. Yeah, this is the 2 sine t. This was the t squared minus 5, right? Is that right now?
Yeah.
Okay, sorry. This is 2 cos t, this is 2t, but the 2's cancel out. Okay, so we're going to put in a cos t over t here, and keep pursuing this. Okay, it looks like I'm going to need the quotient rule to handle that top, right? I've got cos t over t. What's the derivative of cos t over t? Why don't you guys take a moment and solve that? So you're going to take the derivative of cos t over t, and you already have dx dt from earlier. Okay, so low d high is t sine t, and there's a negative, minus high d low, that's just, yeah, it's just basically, high d low is just cos t, right? And this is over low squared. So this is uglier than we thought maybe. It's more involved. There's an extra 2t down on the bottom. That's just from the formula of the day. That's why I had you write the formula down. There's another dx dt that just popped up at the bottom. Okay, and so this comes out to be negative t sine t minus cos t all over 2t cubed. And this is either equal to 0 or undefined. So we're going to set it equal to 0 and undefined to check it out. Okay, so how are we going to get the values that make it undefined?
So 2t cubed.
Yeah, so d squared y dx squared is undefined at t equals 0. Is that point of interest to us? Is that point interesting to us? Or should we just toss it?
Toss it because it's the start.
Yeah, that is actually the starting point of the problem over here. And while it may qualify as a place where there's no concavity, it doesn't qualify as a point of inflection because I'm not comfortable drawing a tangent line at a starting point, per se. So I don't think it's a change in concavity either. There's nothing even on the left. So we're just going to toss it. It's just like a spurious, extraneous sort of thing. Just throw it in the trash. But it's good that we thought about it because we don't always throw this away. Okay, let's look at where d squared y dx squared is 0. This is a little harder to fill in. Okay, a little harder to fill in. So how am I going to figure out the roots of this part right here? I need the roots of this top part. Yeah, let's use our calculator. We'll put it back in regular funky mode. And then we'll graph that and check for zeros. So we'll do a zeros finder thing here. So let's get the graphing calculator back out. We need the roots of that numerator. We need the roots of the numerator. So let's give that a try. Yeah, let's keep it in radians because of the fact that we have a sign in this problem and we're doing calculus. Okay, so let's see here. I'm going back to regular function mode. I call it funky mode because when you press func and you press y equals, that's funky. Okay, so we're going to put in negative t sine t. Hey, now it says x. That's okay. Minus cos x. I need the roots of this thing. And I'm definitely only interested in x's between like negative 10 and 10. We saw that window. That wasn't a very big window, right? But I already have that as Zoom standard, so we're good. Oh, no, I'm sorry. I take that back. We want 0 to pi because these are t values. My bad. So let's change this to 0 and pi because this x really means t here. Okay, graph away. Ooh, did that ever reach 0? Ah, yes, it did. Right here. Yeah.
Mine graphed for a while, and then once
Oh, okay. Did you do something beyond what I did? Were you actually trying to find the zeros? Or?
No, I have the same window and everything, and I grabbed it, and it graphed, and then after it passed this, it just showed the syntax.
Really?
Yeah.
Huh. I wonder if under your window settings we have the exact same thing. So you have 0 and pi,
Yeah.
right? Syntax means you typed it wrong. You sure you typed the function correctly?
Yeah.
Did you, right there where my cursor's blinking, did you use the negative symbol or a minus sign?
Negative.
What about over here? Did you use the subtraction key or the negative key for that one?
Subtraction.
You can reset your calculator. I don't know what else to do. Okay, so I need that point. Don't use trace, right? That thing's horrible. Just do second calc. There's all your goodies again. And let's go to 0. And I learned something. You do not have to do the little wizard by moving your buttons around, okay? I used to always go, left bound, click, and then right scroll, click. Guess what? You don't have to do that. You're between 0 and 2 point something, see the marks? So you can just type 1 or something, and then pick a number slightly to the right of this, or something like 2.9. So I'm going to press 1 for left bound and 2.9 for right bound. And I don't even usually make it guess. So I'll just go 1 for left bound, enter. 2.9 for right bound, enter. Ooh, that was a close one. Look how close it is to the dot. And then for guess, I don't usually do anything. 2.7984. Okay, I did forget to press record there, so I just went ahead and used my calculator to get the rest of that. Okay, let's go to another problem where we find length. So actually, Hunter asked a really good question about traversing once. Okay, so let's go back and look at this picture. One of the drawbacks of parametric mode on the calculator is even not just does it not show you the orientation arrows and the direction, but also you can't really tell if it's drawing the same curve more than once. Okay? So sometimes what happens is the particle will start, and it'll move, and it'll hit the ending point and bounce back. And it will do this 5 or 6 times, even though your timer will only 0 to pi. It could actually be really a happy particle and flying back and forth several times in 0 to pi time. So you have to make sure that you're only looking at one traversing of the curve. Okay? On this problem, you can tell that this is one traversing of the curve because watch. When you put it back into parametric mode, right? And then you set your window again, 0 to pi, and then maybe do a zoom standard. Notice if you change the window setting to 2 pi, you see more curves. See that extra little tail down there? That tells me that by going to 2 pi, the graph is going to just keep going further out. So it's not going to retrace its steps. So I can trust that this really is just one iteration when I go from 0 to pi. So when I change this to pi and I see it stop, it really did stop. It doesn't come back onto itself, I can tell. Okay. If you suspect that the object's moving back and forth, you have to get the smallest time interval for one forward motion if you're going to calculate length. Okay, so let's go ahead and look at this next example. Okay, so on example 2, you're going to consider x equals cos cubed t, y equals sine cubed t, and we're going to let t go from 0 to 2 pi this time. I think we should take a look at it and see what happens. Okay? One thing's for sure, before we graph it, we do know one thing. Everything's going to fit in a very, very small window. What's the smallest x will ever be? 0. No. X is a cosine, basically. What's the smallest cosine ever gets? -1. So x will be between -1 and +1 here, see? And y will be the same. So it's going to be a really small window. Let's give it a try. So turn on your calculator here. Go in here. We're going to change this to cos t and it's quantity cubed, so you actually have to kind of type it like this. Parentheses, cos t, close parentheses, cubed. And then same thing for the sine. Parentheses, sine t, parentheses, close parentheses, cubed. Like that. Okay, and then when you graph it, you won't see much. It's because it's so dang small. Okay? So we got to go into window. We have some changes to make anyway because it said 0 to 2 pi this time, so we have to make sure to update this back to 6.28, yada yada. T-step's fine, but my window's a little too small, like too big technically. I still can't see it. It's in there. It looks like a circle or something. So I'm going to zoom in. Oh, that's cool. And I'm also going to do what's called a zoom square. Does anyone know what that does? Zoom square makes the X and Y tick marks look the same size. Okay? So normally your Y tick marks are a little bit tighter spaced. Now everything's evenly spaced. Each grid line is a perfect square. Okay, what is that thing? That's pretty cool. It's a star. In fact, it's called an asteroid. Not asteroid, like object flying through space, but asteroid, A-S-T-R-O-I-D, meaning star-like shape. Okay, so let's go ahead and put that on our paper. We'll just draw a rough sketch. That is not a complicated graph at all. It goes from 1, 0, to 0, 1, to negative 1, 0, oops, to 0, negative 1, and then back to home plate. How do I know it travels in this order? Well, to be honest, I actually mentally was plugging in 0. So if you plug in 0 for the time, you actually get 1 and 0. If you plug in pi over 2, you actually get 0 and 1, you see. So this actually fits nicely with what I would have seen if I had drawn a table myself. But the orientation is this way. Arrows all the way around. And I'm pretty sure that this thing didn't do a double cycle. That's very important. Did it cycle twice when we weren't aware of it? Like, did it go around 2 times? So here's what I'm talking about. Everybody close your eyes for a second. I'm going to draw a circle. Everybody close your eyes. Got to close your eyes. Don't look. Don't peek. Okay, open your eyes. See, I drew a circle. How many times did I go around the circle? 3.
We don't know.
You don't know. There's no way to know. I actually went around twice. You see some mistakes in there already, Mark. Okay. But what I'm saying is we can't tell from the graphing screen if this went around once or twice. Which means when we set up our limits of integration, if we use 0 to 2 pi, we might get double length. This is so important. It's important in polar too. Please listen. Okay, I lost somebody. If we use 0 to 2 pi, and this thing cycled twice, that means we're going to get double the length. We don't want that. Okay? We want the length, the total length of the curve. So we have to guarantee ourselves that that thing only went around once. So the only way I can think of to do it is to kind of think about cosine and sine. These are both periodic. They do one cycle every 2 pi. Okay? The only time this would spin faster is if this was like a 2t or a 4t or a 5t. Then it could go around 5 times in just 0 to 2 pi. Okay? So the fact that these are 1t's is a clue. Or if you're not comfortable with that and you feel like you might be getting the wrong limits of integration, you could just tell your calculator, hey, let's just graph from 0 to pi over 2 first. Okay, and let's watch it. Here we go. Okay, that was exactly what I expected. It's 1/4 of the shape. I gave it 1/4 of the time to travel. So after seeing it do its job using 0 to pi over 2, I'm pretty sure 0 to 2 pi is just one time around. Very, very important. This is the hardest part of polar, too. When we get to section 10.3, students always want to know, how do I know what my limits of integration are? That is the hardest question by far. Okay? But in this case, it looks like it just went around one time. I'm pretty sure. I'm 100% sure. And so what I'm going to do now is set up my formula. So the length of this curve is going to be 4 times the length just from quadrant 1. Right? Why do 4 integrals? if you can just do 1. And we certainly don't want to integrate through a cusp. So let's just go ahead and do that blue there, okay? We'll just go 0 to pi over 2, and then we'll multiply that by 4. That'll give us the total length. The formula is a little ugly. It's dx dt squared plus dy dt squared dt, and it's all inside a square root like that. And remember, x was cosine t cubed. So what's dx dt? 3.
Negative 3 is sine t squared.
Yeah, negative 3 cosine squared t, right? Because now it's cosine t squared, right? Because you take away a power, times the derivative of the inside, negative sine t. So don't forget the chain rule, and you're bringing the 3 down, so it becomes a 2, right? Okay, that's kind of awkward. Y is sine t quantity cubed. So what's dy dt? 3 sine squared this time, cos t. Okay, what's dx dt squared? 9 cosine to the 4th. Goodness, this is awful. 9 cos to the 4th t, sine squared t? Don't worry, it all cleans up in the end. dy dt squared is 9 sine to the 4th t cosine squared t. Okay, it's time to put these into our integral. If you look at the formula, see there is a square right here. See that? These get squared before they get added. Okay. So let's give it a try here. Let's go. The length of the curve is the integral, or excuse me, 4 times the integral from 0 to pi over 2 square root of garbage plus garbage. Slightly different garbage there. It's all garbage. Okay, that's pretty ugly. Man, maybe we could pull something out, right? I see a 9 and it's being square rooted. Actually, you're probably smart to factor this anyway, so let's go ahead and factor out anything we can. First out of the radicand, then out of the square root. But I see that they both contain a 9, they both have a cos squared, and they both have a sine squared. And if I pull that out, I'm left with Mama's theorem on the inside. Look at that. Hello, Mama. Okay? It's funny how that just pops up. You know, it's like your mom's always around, right? Okay. So this is 1. Yes, this inside part here is just 1. In fact, we can even square root this 9 cos squared sine squared. This is working out really well for us here. This is just 3 cos t sine t. Pull the 3 out and you have a 12 right there. And this one can be solved just by regular trig substitution, or just substitution. So you can just let u be sine t, for example. du is perfect. Look at this. Cos t dt. It doesn't get any better than that. L is 12 times the integral of u du. Remember, these are t values, not u values, as you know. So we get L equals 12 times 1/2 u squared from 0 to pi over 2, and these are t's. In other words, 6 times, and then we have sine squared pi over 2 minus sine squared 0. What's sine of pi over 2? 1. Sine 0 is 0. Interesting. So the asteroid has length 6. 1.5 here, 1.5 here, 1.5 here, 1.5 here. So this is our last formula of the day, and an example of how to use it, and we're done with 10.1, okay? So there are a couple things that you might have to think about in the homework. Like I gave you 2 nights to do the homework. It's due Friday. I sent it to you by Edmodo, okay? I already sent it to you. But there are a couple things you have to think about, like, let's go back to example 1. There's something I didn't point out that I'd like to now. Why is it that when we were seeking this blue tangent line, horizontal tangent line, right here, we were seeking this blue horizontal line, right? But we got away with setting dy dx equals 0, and we found out that that means the same thing as dy dt equals 0. What was my argument for that? What was my logic in that?
At the top of the paragraph.
Yeah, dy dx is this complicated mess, right? But since this is a fraction that's equal to 0, we can assume the top is equal to 0. Do these mean the exact same thing? Technically not. Dy dx equals 0 means that here on this track, there is a horizontal tangent. So think, first time, think of this as a street. Okay, it's like a hiking trail maybe. It's like a hiking trail. And then there's, or maybe it's like a hill to climb. Okay? So nothing's moving, it's just a hill. There it is. Dy dx equals 0 represents the peak of the hill. Nobody's moving. Okay? Dy dt is a moving object. That's the vertical speed. Okay? So this is like the vertical velocity of something moving on this curve, dy dt. When the object reaches the top of the hill, it needs to start going back down. So its vertical component of velocity is 0. That's what this means. So this means the vertical velocity is 0, and this means the hill has a peak. They're not exactly the same meaning, even though they both mean the same thing in space. They don't have the same meaning in words. This means that where is the peak of the hill? And this means if you're climbing the hill, when do you stop climbing? You see? They're really the same question disguised, but the symbolism is different. This means at what time do we stop moving up and down? This means at what place is there a peak? So you need to know the difference. Okay? All right. So that's the end of the lesson. When we do the Q&A, we'll do a very thorough job because there is a little bit of that kind of critical thinking in there. What about set equal to 0, that kind of thing?